Hello, my name's Peter Lawrey, and I will be talking today about some real-world use cases for Lambdas. Um, when I looked into Lambdas in Java 8, most of the examples I saw were for things that, or for code that wasn't real production code. It was just examples of what you could do. But in many cases, I found them unconvincing, partly because often I would look at it and say, well, you could do that with a loop and probably with less code, so why would you use a Lambda to do the same thing? However, about 6 months ago, we were given we had a client who had the task of migrating a C# application that used LINQ quite a lot, and the natural choice to switch this application was to go straight to Java 8. That would save us having to rewrite a lot of functional programming code. And out of the 25,000 lines of code, about 2,000 are Lambda-based code. So, so a lot of the 90% of the code is not, but there's certainly plenty of examples in there of code that I think works quite elegantly. Some code that, when we translated it, looked quite horrible and did some strange things. So we were talking about not only what looks good in Lambdas, but also what sort of things you should avoid doing it with Lambdas. So here's a simple example. In this case, it's a bit like using contains on a collection. In a collection, you can look for a particular matching element, but in this case, you've got the option to look for an element that fits a certain criteria. In this case, you provide a predicate and it will tell you if any element in the list for which this predicate is true. This one's a little bit surprising, I thought, but anyway, there's a lot of deep copying going on in the application the way it was written. I tend to try and go through hoops to avoid this, but it made for a fairly simple example here where it goes through each of the elements in the list. It clones each element and then creates another list with that cloned set. Again, in Java, you could do that with about 3 lines of code in a loop, but here it's a one-liner. This one's a sort of an odd one in a way, because the whole point of functional programming is to avoid side effects. You want to minimize side effects. But we actually found that quite a few examples where there were side effects. Either a mutable state was being altered inside a Lambda, or as in this case, the entire purpose of this Lambda is to throw an exception if any of the elements is not valid. So clearly that's a side effect. Another one that's a bit odd is that there was a lot of use in big decimal. Now, if you want to sum up integers or doubles, that's very simple. You just use sum. However, for big decimal, it's a little bit uglier. You need to use a reduce function to sum all the elements of a collection of big decimals. In this case, what the reduce does is it takes 3 parts. And part of the complexity that you find in many of these more advanced cases is due to the fact that it needs to support concurrent computation. So in fact, this function would be simpler if it didn't need to support concurrent computation. And you actually see examples where 2 of the methods that you have to provide do almost the same thing, but in a slightly different way. So for example, here, the first expression is what do we start with? What collection or value do we start with? And since we're adding, the first thing we start with is a 0. Then we go through and add, we take the previous value. This is the second reduce argument. We take the previous value and the current value that we're working on, and then we add in another big decimal. Now, finally, we may have split this across multiple threads. We haven't, but we might have done. And to collect all those big decimal results, we need to add them together. And so that's why there's this almost duplicated expression that appears. This is a repeating pattern that you see where you're sort of not sure, why am I creating two methods that are kind of similar to each other? But it's because of this need to support parallel streams. Now, this is a slightly more complicated example of sorting. Now, in this case, we're first sorting a collection based on a dereferenced field, which is the date that sits inside some other object. And then we're sorting based on a symbol, which in this case is called a QSIP. And finally, we're sorting by the quantity, but in reverse order. So we want decreasing quantity sizes. And you can write all of that as a single expression. You can compose your collection comparators. This can be quite powerful because you can see quite clearly how you're building this up. Now, if you're used to writing comparators for multiple fields, it doesn't seem like such an overhead, but certainly for a lot of people that don't quite understand how to do that chaining themselves, this is much more elegant, and particularly when you've got the reversed case. When you write your own comparators, switching around the order is quite subtle. You either maybe replace a greater than with a less than, or you swap the two arguments around, but it's something that's quite easy to miss, that this is a field that you want the decreasing order rather than the increasing order. And so in this case, it's much clearer. You have this reversed option. This is another example of a more complex lambda where you're using grouping. So firstly, we filter the values of a map in this case. Then we go through and find all the things where you have a non-zero quantity. So we want to discard all of those. And then group them by some key. So as you can see, then you end up with a map of lists of elements that were the values of another map. It's quite powerful. You can write that in just a few lines of code. This one's very similar, except instead we want to retain the entire entry. And this is where a side effect is coming into it. Because as you can see, the for each is in fact altering a variable that's been passed in, or in this case, a map that's been passed in. And that's because there aren't the sort of collectors available that will support this in terms of building a map from a sequence of entries. Although you could write one. Now, we're starting to get into the antipatterns. Now, these are patterns that came up as a result of writing this code and translating it from the C#. And initially, the priority is, of course, getting it to work and behave like the original C# program. And less worried about, well, is this optimal? Is this elegant? And so there's some cases which came up that weren't elegant. And particularly, this is a good example of that, where it's functionally correct, but it sort of defeats a lot of the purpose of using streams. The whole idea of using streams is that for as long as possible, you don't accumulate your results. You're streaming data. So it's like a river. You want it to start at the start and run all the way to the end without any blockages, and you will get usually the best performance, but also you get the simplest solution. But in this case, what's happened is that halfway through, after doing the filtering, it's collected into a list and then broken up into a stream again, because that's what for each does on the very last line. So it's been accumulated into a big dam, and then that dam doesn't do anything terribly useful, and then it gets passed on again to another stream. And in fact, you can do the same thing just by removing that collect, just stripping out the collect itself. It would still compile, and in fact it would run more efficiently because it didn't create a list that wasn't required. And in fact, to do it more elegantly, instead of having such a complex for each, you can break that down and eliminate the adding to an existing list. You want to return a new list most of the time. And so in this case, the map extracts out the elements from everything in the stream that you're interested in, and then collects it into a new list which has all of the elements you're interested in. Here's another example of an antipattern. You read it and you can see its intent, but unfortunately the way it's implemented defeats the purpose to some degree. So in this case, what it's doing is it's saying, I want to sort by date. So I want to get all my trades and I want to sort them by date. And then once I've finished them, I want to put them into a map, which has all the dates and trades for those dates. There's a problem with this, is that the default map, although I haven't read the documentation, so I'm not sure, but it can produce a hash map. So if you sort all your keys before putting them into a hash map, they're no longer sorted. A hash map is not sorted. So the sorting here doesn't actually do anything, or it's not guaranteed to do anything useful. And so it is implying some behavior there that's not actually happening. There's a way around this, is that you don't bother sorting it in the first place. Instead, what you do is you add these elements to a map that sorts the keys naturally. And the way to do that is another one of these three-part expressions where you give it the elements that you want to add, the collection you want it to use, or something that will create the collection you want to use. And in this case, it's a new on a tree map, which is, I always found this sort of odd syntax, but it works because it was new tree map, now it's tree map new. And then you do toList. And what this toList does is it says, what do I do with all the elements that are for the same key? So here's another antipattern. The problem with this is that it implies that you're going to sort by one, and then preserve the order and sort by another field, and then preserve the order and then sort by another field. Now, this is not only inefficient because you're sorting it 3 different times, but there's no real guarantee, or it's not clear that there's a guarantee that the previous fields will be preserved in terms of their relative orders. I wouldn't be surprised if, say, this works for stream for some reason, for technical reason, but then if you do parallel stream, because it has to do it concurrently, it suddenly breaks. A solution to this is to have it sort it once, using the comparator that will go through all 3 fields. So this is similar to the previous example where you compose a comparator for 3 fields. Now, one of the things to note is that when you sort individually, you're putting the least important field first through to the most important field, because the last one is the one that's most important. When you're building your comparator, you do it the other way around. You compare by the most important field, and if that matches, you give it the second most important field, and if that matches, you give it the third most important field. Okay, so this is so we're starting to get out of the real examples, and this is actually to do with a more common interview style question, which is, give me the 20 most common words in a text file. Now, you can write this in natural Java and Java 7, but it's actually quite long and convoluted, and one of the things you'll note is that a lot of what you're doing actually doesn't have anything to do with the problem. You're actually having to work out whether you have to do a lot of manipulation with collections. But in this case, this code, apart from being a very long one-liner, is actually showing you pretty much only what you need to know in terms of what it's doing. All of the manipulation underneath to make this really work as a series of collections is hidden from you, with the exception of the bit that's in bold. Now, the current version of the compiler actually requires you to qualify the types involved here, and you get this rather surprisingly ugly syntax, in my opinion. So, interestingly enough, for get value, you have to specify what the key and value types are. But 2 lines later, for get key, it can work it out for you, which is interesting. So what is this doing? This one's interesting because it's doing a lot of things and shows you a lot of examples of what you can do with lambdas. The very first one is that it turns, the file lines turns an entire file of lines into a stream. So you have this continuous stream that's streaming into your application as a line by line. So then you can manipulate it as a stream. Now, some of you may seen parallel stream. You can take a collection and call parallel stream on it rather than stream. Now what parallel stream does is it creates a stream which is for parallel use. But there is another option which is just on stream itself which says parallel, which says up to this point it might not have been parallel, but from now on it is. So this is using just dot parallel on a stream is how you can switch it to running concurrent execution. So at this point, the next 3 lines are actually run distributed across all your CPUs. Right? Just by putting that extra method in there, which is quite nice. Then you come across a thing called flat map. Now flat map is a bit odd if you're not used to this kind of terminology. What it does is it says, I want to take all the elements that you produce and make them elements of the stream. So it's not like if you construct a list of lists, I want to decompose it into just a list by concatenating them all together. So what this is doing is it's producing a stream of words from each line. So I take in a line, I now want to produce a stream of words, and those words become part of my now completely flat stream. I don't have a stream of lists of words. I don't have a stream of streams of words. I have just a stream of words. And that's what this flat means. Map by itself would just do a translation 1 for 1, whereas flat map can produce 0 or more. So that's a kind of interesting thing, is that a flat map, you can have a whole lot of flat maps that actually can produce 0 elements, so you can end up with less elements. But generally speaking, it's used to create more elements, as it does in this case. You turn lines into words. Then the next line, I want to collect all this stream of words that's coming down, and I want to group them by word. So a bit like the grouping by I did before, where you group the, say, trades by date. Now I want to group all the words together. I don't want to do any translation on those words. I just want to turn them into keys. So that's what that W arrow W does. It just takes a value and returns it and says that's going to be my key now. And I don't want to accumulate all these words in a list. That's a bit redundant. All I want to do is count them. And there's a function in collectors that will just count the elements. Instead of creating a list of words, in this case it will just create a long, which is the number of duplicates of this word. So out of this comes a map of words and count. So in just 3 lines. And it keeps track of when the first word comes in, and the other thing it's done, which is really cool, is that at this point it's accumulated all the results across multiple threads. So it's taken all these lines, spread it across all the threads on my box. They've broken up all the words. Each one of them's produced some sort of frequency count map. And at this point, it's gone and said, all right, for all these frequency count maps, I now want to accumulate them, so I now have one map with all the words with their total frequencies. That's quite amazing that you can do that in just in this case, half a line. Okay, so now I take this entry set because now I want these things to be sorted. So I take the entry set of what I produced and turn it into a stream. And then I say, right, now I want to sort by value, which is the count. And I want that count to be in reverse order, so that the first ones will have the highest count, and it'll go down to the lowest count. So I've sorted them, but I don't want all of them. I only want 20, the top 20. So I set a limit of 20. So as soon as it's got 20, although because it's sorting, it probably has to sort, it does have to sort them all. So once I've got 20, elements, then they're the entries that I'm interested in. Except, and now this is where I use a map rather than a flat map, I'm not interested in the entire entry, I just need the key. So for each entry, it gets the key, which is the word, and then I turn it into a list. So all of this code has now produced a list of the top 20 words in descending order. So as my friend suggested, we should, in a more realistic example, you might want to break this up so that you can see what each stage of the process is doing by giving variable names. That would make it a lot clearer as to what it's doing. It almost certainly needs quite a lot of comments because, as you heard, the explanation for what a few lines of code is doing is quite long. But it's also a surprisingly powerful example. Here's a couple of more examples of what not to do with streams. These are possibly attempts to really use, I want to use, streams are great, I have to use them. But as you can see, they're probably not necessary. So in this first, the top example, it's taken a list of balances, it's turned them into a stream, then collected them into a list, which of course it was already, and then adds them all into another list. If you took out all the code there to do with streams, it would do the same thing, but probably more efficiently. Now in the second example, what it's doing is it's adding all the contents of two lists together. And again, it's used streams to do it, but again, probably just using add all would have done it. Add, all trades.add all trades 1, add all trades.add all trades 2. And that would have accumulated all of the trades into this resulting collection. So that's one of the things that streams doesn't do quite as elegantly is taking multiple stream inputs and concatenating them together. You could do this with streams. You could actually have a stream of collections and then do a flat map on each one and then collect them. You're starting to get quite convoluted, and there are cases where it just makes sense to use the same methods that you're used to in Java 7. Now, as a slight bonus topic, you've got another thing that comes out of the Streams API is the use of optional. Optional is a way of encouraging you to handle what in the past might have been a null result. So in many cases, if you look for an element and the element doesn't exist in a collection, it's quite common to return null. So get, for example, map.get will return null if that key doesn't exist. And so to get around this approach and having to check for nulls, and people forget to check for nulls, and you end up with a null pointer exception, they came up with this API called optional. Now, optional is a simple collection wrapper. You can have 0 elements, which means it's not present, or you can have 1 element, and that's the answer. Now, it has a number of helper methods which allow you to set defaults, which say, if you didn't get a result, what do I want it to return instead? Like a default value for something that didn't come up. And interestingly enough, you can pass in null, which means that all the advantages that you got from using optional have been thrown away, and you've gone back to the old if it's not null check. So in this case, what it's done is it find first returns an optional, and you can check to see whether there was a result or not, and if there was a result, what to do with it. Or you can do this, which is not a good idea, but is perhaps a bit of a hack or a workaround, which allows the rest of your code to work the way it always has in terms of null checks. Here's an even more convoluted example where it starts off with an optional and says, I don't really like optional, so I'm going to create a local variable which is my non-optional, and then say if it's present, then go and get the value, and then if that returned a value that's not null, I'll go and check that for that. So clearly, a lot of that code is redundant if you just used optional the way it was intended to be used. But I can imagine there will be quite a lot of code like this where people are not confident in using optional and they just need the code to work, so they reduce it back to the things that they're familiar with, which is doing a null check. And so I think we might have time for questions. Oh, yes. Do we need a microphone? Yes, they're easy to detect if you know what sort of bugs to look for. One of the problems with Lambdas is that people don't have the experience of saying, if you've only worked in Java that is, they don't have the experience to know what sort of things you shouldn't be doing in Lambdas, what to look for. And I believe that support will come into place. There is a lot of support already for refactoring. So if you've got something that has a loop and it could be refactored into a Lambda, there are IDEs that can automatically translate you either way to reduce it into such a Lambda. But I think it will take some time for people to recognize what are the common mistakes people make when using things like the Streams API, and what sort of corrections you could do. So a lot of cases, it's also handy to have an auto fix. So so in this case, in this example, the collect is redundant. So not only should it detect that it is redundant, but it could also just take it out for you, give you the option to remove it for you so that you don't have it in there.
Okay, so currently you don't know anything about some support from the compiler to IDE or some find bugs check status plugin to detect this kind of behaviors?
Not yet, not that I know of, but I expect that it will come. It could probably come in the next 6 months. As, like I said, a lot of people are curious about Lambdas and haven't been, certainly not in the Java space, maybe if they come from the C# world, but not in the Java space, do people are using it long enough to say, well, this is a common bug that I would like to avoid happening in my code.
And in C#, because you said that this project was rewritten from C#, so do you have any experience from C#? Are there any support on this, on C# side?
I don't know the answer to that, to be honest. I'm not as familiar with the C# toolset.
Oh, okay, so I thought that you are also with, okay.
No, we can read C#, but being able to use it, write it in an optimal fashion, and what are the best tools to use, that's not really.
Okay, thank you.
I was wondering how you organize your code, because, for example, the example with summing big decimal, it was quite verbose. So do you create some kind of utility classes for functional expressions, or do you just write it out full each time?
Yes, that's one of the things that we've been doing a lot more recently, is we've been creating lots of helper methods for these things. So, for example, there's a sum helper method that will take a collection of big decimals and sum them up, rather than repeating this pattern again and again. Another common one is filtering. So this is a bit more complicated, but in many cases, all we want to do is filter all the elements that match a certain predicate and create another list of those. Also, in many cases, we are not returning one, but two lists. So we want to split them. So we have a list, we apply a filter on it, but we also want the list of all the elements that didn't match that filter. We want to split it into ones that match and ones that don't. Streams don't do that quite so elegantly, but we use Lambdas, but we don't use streams in that case, because we end up with a for loop which will add it to one or two of two collections.
Thank you. So maybe that's an idea for an open source project to create such utilities.
Yes, yes. I think if we get enough of these examples, we'll probably turn it into a project of its own. Some open source examples of how to write some trivial filters. Another one is mapping. So often you want to do a translation on every element of a collection. At the moment, you have to do .stream, .map, the predicate, and then collect it probably into a list. It'd be nice to do that as map. Just map, apply, list, and the mapping, and that's it. And then it takes away a lot of that boilerplate. It's kind of a shame. And one of the things that C# does is that they tend to throw a lot more permutations into their libraries and make them a bit more complicated, but they also have more options. So, for example, they don't have .collect to list, they just have to list. They say, well, this is a common pattern. I just want to have a method that to lists. this stream. The other thing they do is they weren't so worried about backward compatibility, partly because it's been established for a while, but it's also a general trend in C# is that to go from one major version to another, they don't worry about that quite so much, and so that there's not a dot stream method at all. It isn't actually required. So again, that took out a bit of the complexity. The other thing is they handle getters and setters with a lot more syntactic sugar, so that shortens that bit as well. So it's not it's more verbose than the C# equivalent, but it's still pretty close in terms of the expressive power and what you can do with it.
Having converted stream into a parallel one using the dot parallel method, is there a way to deliberately convert it back?
Yeah, okay. What I do know is that IntelliJ has the option to detect loops that could be turned into streams, and it also has the option to take a streamed piece of code and turn it back into loops again, the original loops. Is that what you meant?
No, I meant if I would use the dot parallel method,
Oh, yes.
therefore making this stream a parallel one, is
Yes.
there a way to make it non-parallel?
Only by using the dot collect. So in fact, that may be one legitimate reason for doing this. So if, for example, that instead of dot stream, that was dot parallel, then what would happen is that the collect would bring it all together, and at that point, it would go back to being serial again. So this for each, even if dot parallel was at the top, the for each itself would be single-threaded. The reason we might want to do that is maybe trades isn't a thread-safe collection, for example. That's another thing to watch out for. When you use dot parallel, you have to make sure that the operations you're performing are now thread-safe. The code looks exactly the same. It probably works most of the time, but it's very easy to introduce concurrency bugs by not being aware of this. And the reason this matters is that so group by, for example, there's actually a grouping by concurrent. So there's a different method for optimally collecting concurrent results. And I'm not sure about the details, but I believe that instead of returning a hash map, it returns a concurrent hash map, because the concurrent hash map can be updated across multiple threads.
Okay, did you attempt to use Guava for some of the operations? Because from our experience, it turns out that there are some cases where just using Guava with the Java 8 techniques like functions, predicates as lambdas, the code looks really nicer than when you just do this like stream and then collect to list every time. And the iterables and fluent iterable from Guava are a really nice solution, like in terms of the utility classes you mentioned. So it's not always necessary to write your own utility classes, but you can also check if there isn't something proper in Guava.
Yes. No, that's a very good suggestion here. Guava has been doing it for longer, so it wouldn't surprise me that they would have options that are more elegant than the Streams API they added. One of the things about Streams is when you look at the number of methods that they've added to support Streams, it is a very large API already, and I believe a lot of options were taken out when they did the final release. They weren't too sure about the functionality they were providing. They may add it in the future, but it does mean that there's a lot of things they don't support. One of the more obvious ones is zip. They don't do that. That's probably the most complained about feature that's missing that I've seen.
Someone else? So thank you so much for your speech, Mr. Lawrey.